All right, guys. So everything we're going to cover today is about TileDB Embedded. This is the storage engine of TileDB, and everything is going to be on the open source aspects of our company. Nothing closed sourced today. Who is this webinar for? Well, it's going to be useful to you if you want to learn more about storage fundamentals. So it's not just about TileDB. I'm going to explain why things work very well and why we took certain decisions. So you will learn some storage fundamentals if you're not familiar with them, what makes something being performant, what is the layout, what is compression and all of that. This is also for you if you are very tired of using inefficient data formats. You have used, for example, stuff in geospatial and genomics and they don't work, they're not very interoperable. You're going to see that TileDB can subsume all or most, if not all. And I'm going to present a lot of features that you can find in TileDB Embedded. And finally, if you just want to store and access data very, very efficiently in any kind of data and potentially multiple types of data with a single engine, this webinar is definitely for you. A disclaimer that I always use now in my presentations. So all the credit for the amazing work I'm going to describe goes to our powerful team. You can see them here. We are hiring. So if you like what we do and you think that your work is relevant to what we do, please reach out to us. I'm going to show you some links later. But please know that I am the exclusive recipient of complaints. So if anything breaks, if there is any issue with the software or the company, just come to me. All right, a few things about who we are in case you don't know us already. TileDB is a research project I started when I worked at Intel Labs and MIT back in 2014. We had some fair success with it, and we decided to spin it out into its own company, which happened in 2017. The software itself, as well as the team, has very deep roots at the intersection of high-performance computing, databases, and data science. We have raised so far over $20 million. We are quite well capitalized, and we have an amazing investor team. We're very grateful to them. Currently, we're 40 members in the team. And in addition, of course, to having very strong software engineers, we also have domain experts. We're working in a broad range of applications, from genomics to imaging to LiDAR to any kind of geospatial. So we do have domain experts to guide us. And we have a lot of traction with telecommunication companies, pharmas, hospitals, and other scientific organizations. We do a lot of things under the radar, but you will soon see all the case studies and everything we have been working on in the past couple of years. So what is TileDB in a nutshell before I get into the details? First of all, it's a library. It's built in C++, and it stores and accesses multidimensional arrays. So a multidimensional array looks like this. It comes in two flavors. The first is the dense array. It has some dimensions here, D1, D2, of integral types in this case. This is a cell, like a little square, it's a cell. You can store pretty much anything you like inside the cell. And you have attributes inside the cell. These are the values. You can have different types of values inside the cells. And you can have any kind of array metadata. These are key value pairs. And then the sparse array is very similar to the dense, but the majority of the cells could be empty, completely empty. The dimensions could be infinite. You can have strings, you can have floats, so much more flexibility with the sparse arrays. And you may even have multiplicities. And again, you have non-empty cells with attributes and so on and so forth. So this is the data structure. You're going to understand why this is powerful very soon. So I'm going to delve into the details. But this is what TileDB Embedded does. Like it sounds very simple. It stores and accesses data in this model. And not most importantly, but equally importantly, it allows for very fast slicing. Slicing means grabbing any subarray, any subset of those cells. Very fast. That's what it is designed to do at its core. And of course, we build a lot of other stuff on top, but that's the functionality of an array engine. TileDB is an array engine. So again, a few of the features at a glance, and I'm going to elaborate on everything as we go. It has great performance. It's built in C++. It's parallelized. It's a columnar format. I'm going to explain all of that. It has compressors. It has indexes like R-trees. It supports rapid updates and versioning, very important features. It's lock-free, parallel writes, and so on and so forth. I'm going to show you all of that. By the way, you can find the repo here on GitHub. It offers extreme interoperability. We have numerous APIs, a lot of integrations. We support pretty much all backends for storage. And finally, it is optimized for the cloud. So the architectural decisions we took, especially around the format and how the engine works, so it happened that it works perfectly on the cloud. Like the way we designed it, it's really cloud native by definition. Also in the software stack, this is what you should anticipate. You have all the backends at the bottom, any backend. And if we're missing something, just ping us and let us know what to integrate with. At the very top, a lot of APIs, a lot of languages, a lot of tools, integrations with databases, integrations with Spark, Dask, Arrow, and so on. So for even some domain-specific tools. Again, if we're missing something, just ping us. And TileDB is in the middle, TileDB Embedded. It handles all the storage and access. And we take it to the extreme to integrate with all those tools at the top, and we adopt zero-copy techniques. We do that very efficiently, okay? Very, very efficiently. We take it one step further. It's not a naive integration with all those tools. Our team does the integration. We may be using Arrow for certain things, for certain other things, we do our own things. The integration itself is sophisticated, and we put a lot of effort to do it. All right, so this is just some preliminary information, but here's the actual agenda for the webinar. I'm going to elaborate on why we chose that data structure. I just told you that TileDB works with arrays, but why? I'm going to explain a lot of the basics. I'm going to show you usage and everything. Then I'm going to delve a little bit into the more internal stuff and more advanced features. I will be showing examples throughout. I'm going to tell you about the work in progress because we have an amazing team that are working very, very hard for all those features, and we're doing a lot of cool stuff that is coming up. And then I'm going to give you only a very high level of a comparison to other formats so that you understand after you have seen this webinar, you can understand a little bit how we differ from the others and what our real strengths are versus the competition. You can find our docs here at docs.tiledb.com. Everything that appears in this webinar is going to go into the docs. So expect a little bit of refactoring in our docs. The docs already contain good information, but very soon we're going to enhance them. So always go check the docs, and if we're missing something, let us know, because we're very serious about our documentation. All right, so why arrays? Think about any kind of data that you may have. Could be genomics, could be LiDAR, could be images. It doesn't matter what it is, right? It doesn't matter what kind of jargon you use for your data and the fields. Regardless of your data, when you store it, you need to store it in one-dimensional storage medium. It's a medium which is addressable by a single sequence of byte offsets. That's what it is. And also, regardless of what kind of algorithm you have, it may be a SQL operation, it could be linear algebra, like a matrix multiplication, it could be anything you can imagine. The algorithm itself, like especially parallelized algorithms, they're usually expressed as a graph, as a task graph, right? And each task slices a portion of this data in order to work on it, either in parallel or out of core. Out of core means when the data cannot fit in memory in its entirety, and you're gonna create a block-based algorithm. I'm gonna slice it one portion, bring it in, process it within my memory constraints, and the next block, and the next block, and so on and so forth. So regardless, what I'm saying here is a set of axioms. You cannot get away from those, regardless of your application. Now, having said that, the performance is absolutely dictated by the locality of the result that you're asking in this one-dimensional medium. For example, this is good, right? Suppose that you have a particular application, and one of the tasks slices these two blocks. It doesn't need to be one contiguous. If it's one contiguous block, excellent. But even if it is a small, reasonable number of contiguous blocks, you're still okay. But this is not okay, right? If your algorithm is slicing many discontinuous blocks from the one-dimensional storage medium, performance is going to be degraded, right? So performance is absolutely dictated by where the result is located. So now, what do arrays do? Arrays give you a super flexible way, and of course, I'm going to explain how this is done, but for now, arrays give you a super flexible way to lay out the data, even if you have multiple aspects that you're asking on or multiple dimensions, to store the data in the medium so that it helps the query results. That's it. that it's that generic. It doesn't matter what application you have, but arrays will give you superb flexibility regardless of the application to lay out the data with a couple of parameters that I'm going to explain in a way that your queries are going to be helped enormously. And just a couple of bullets to tell you what more specific aspects arrays are flexible at. It's going to allow you to give different importance on different aspects of your query, different dimensions. It's going to give you the flexibility to choose whether to store the coordinates of the cells or not. It's going to give you the opportunity to do fast search through indexes. All these are hidden from you. The arrays and the array engine will do it. It's going to allow you to compress and encrypt. Again, all transparent to you guys. It's going to abstract all the engineering magic. It's not just the format. When I say arrays, I mean the format and the engine together, right? Together, the array engine. And most importantly for us and for the vision of the company and for what we are evangelizing is that since arrays can do all of that, they can unify the data model for all applications. And this can give us universality, right? This structure can give us universality. So for those wondering, arrays do subsume data frames. For example, this is the data frame with 4 columns. I have 2 options, or basically 2 options. Like if I was to store this in an array, I would either store it as a bunch of vectors, so one-dimensional arrays, and that would give me very fast slicing on row IDs. Like I want the first 1,000 rows to be sent to this worker, while the second 1,000 of rows being sent to that worker. So this slicing is going to be super fast, and the workers are going to get the particular rows to work on. However, if I know that my workload involves a lot of slicing on 2 of those columns over here, like, I don't know, stock and time, right? I know for a fact that 99% of my workloads are going to be on those 2, and then there's going to be some extra filtering. Then I can choose those columns, model them as dimensions, and then every row becomes a point in a 2-dimensional space. And then I can slice very fast in this 2-dimensional space. So in other words, we're indexing those 2 columns by making them dimensions, and we allow fast slicing in multiple dimensions at the same time. So data frames and all the data frame functionality can be subsumed by arrays. All right, so arrays are universal. I'm going to give you just a couple of applications that we're working on. I'm not going to cover them in this webinar, but so that you know, we are working on all of those, and there are going to be subsequent webinars. So LiDAR, this is 3-dimensional sparse arrays. SAR, I'm just going to go through them very quickly. Population genomics, single-cell genomics, biomedical imaging, time series, weather, graphs, video, key values, and even flat files. We do some very cool stuff by storing file blobs as arrays, inheriting everything we do with arrays. But this is for another webinar. All right, so I will start getting into the basics. So here's a simple 2-dimensional dense array. This is how it looks like on the disk. So it's a hierarchical format, multi-file. The array itself is a directory. It has subdirectories. The schema goes here, and the schema contains information like how many dimensions, what are the types of the attributes, and so on and so forth. And you see that all those T's here are timestamps. This is what will help us do versioning and time traveling. This is a fragment over here. A fragment contains all the information about one batched write. So if I wrote this whole thing, this is one fragment. If I write again, it's a different fragment. And these are all timestamped so that I can time travel. And this is the attribute data. Like all these values, 1, 2, 3, 4, 5, and so on and so forth, they're serialized somehow, which I'm going to tell you later about in this file. And this is where they're chunked, compressed, and so on and so forth. But this is the attribute file. And that's it. So I'm going to show it to you. So here in the dense basics. So suppose we import the libraries. I'm not going to run this. I have run it already so that we expedite it a little bit. So we're at 2.4, fresh out of the oven. That's how I create it. I create some dimensions. I create the domain. I create an attribute. It's integer. I create a schema. I'm saying that this is dense over here. And I just create it. And this will create the array folder. And these will be the contents. Initially empty, so no fragment, but the schema here. I can read the schema so that you see it. So I have 2 dimensions. I have 1 attribute. I'm going to explain this later. It's dense. And then I'm going to prepare a 2-dimensional array with NumPy to store into the array. So I just open it in write mode and I write it like this. So I write in the whole domain, I write this because my domain is 4x4. Okay. And then after we inspect it, we see that a fragment got created. So this is the fragment right here. These timestamps are milliseconds since epoch. Okay. And this is the attribute file. I'm going to explain what fragment metadata is later. Okay. And then if I want to read it, I open it and then I just use NumPy-like notation and I slice it. That's it. I slice it and I slice the attribute because the result always returns an ordered dictionary of NumPy arrays, 1 per attribute. And I'm going to get into this in a bit. Okay. And then I can also slice, very NumPy-like. So I can slice this. These are open-ended on the right side, like NumPy, these ranges. And I can even do a multi-range query. So I can use a multi-index to slice rows 1, 2, and 4, and then slice columns 1, 2, 3. And the result is a cross product of this in a single array. Okay. And this is it. This is the dense array. Now let's check out the sparse array. So the sparse array is similar, but it may have empty cells, and we never materialize the empty cells. We materialize only the non-empty. So structure is similar. Schema here, as before. And the fragment here. This is the attribute data. This is going to contain only 1, 2, 3, 4, 5, 6, nothing else. And then these are the coordinate files, also split per dimension. So these are all the X coordinates. These are all the Y coordinates, or row coordinates and column coordinates, right? It's a columnar format. And that's it. Like, and we need this because we need to filter on those later because we don't know where exactly they are, the non-empty cells. We don't know the distribution. For dense arrays, we do. So we don't need to store them. I'm going to show you later that we can slice without that knowledge. But here we need them. All right, so let me show it to you. Over here. Very similar ideas. The array is created very, very similarly. The difference is here. Sparse equals true. And as before, we can check out the schema. I'm just going through this quickly. This is how we write. We write vectors of NumPy, like NumPy vectors. 1 for the attribute, 1 for the rows, 1 for the columns. That's how we write to sparse arrays. I just want you to visualize this. We never materialize the zeros, but it looks exactly like the example in the slides. So TileDB will only store the non-zeros from this particular example. So you can ignore it. It's just for visualization purposes. But this is how we write. We open the array in write mode, and we pass the row and column vectors here as indices. This is where we're writing effectively. And the data, similar to the dense arrays here, the attribute data. Similar idea, a fragment is created, but D0, D1 stand for the coordinates now. And we can open it and we can slice it. We get back an ordered dictionary, as I mentioned, and I'm going to show you how to visualize this a little bit later because we have other functionality as well. But here this returns, the row coordinates, the column coordinates, and the attribute. If you zip them, then you're going to get the actual row column value. You can slice it as before, same idea. You can multi-slice it. You can use a multi-index as before. So almost a unified way to use dense and sparse arrays, single engine. All right. So TileDB also supports groups. This is very simple. It's like a folder hierarchy with a special name, the special file here, so that TileDB knows that this is a group. And this is a very nice way of grouping arrays and grouping other groups together, just so that you have tidy files on your system. Very simple to demonstrate here. I can do it with the sparse arrays. You create a group, you create another group just using path notation, and you can create the same array as I created above, but inside this nested group. And if you see the tree hierarchy, you can see that this is the top level group, a nested group, and an array inside the nested group. So nothing crazy here. Okay, TileDB also supports arbitrary key value metadata stored with the array. Very important so that you don't lose your arrays and you keep the metadata along with the data in the same place, and also take advantage of versioning, time traveling. Everything I'm going to talk about around data versioning applies also to array metadata. So the key is typically a string and the value can be anything. And the metadata go here. You see there's this folder, and also similar idea for the naming, because TileDB can find very easily, I'm going to tell you later, through the names, it can prune a lot of fragments, a lot of metadata versions so that it expedites the query. So it's important to keep the timestamps in the name. There is a reason for that. And again, I'm going to show it to you. Sparse arrays is fine. So this is how you write metadata. You open the array in the write mode, and you just use this .meta member here. And again, it's a string, and this is the key and the value. I can show you, I'm showing you here different types of values. Always the key is a string. And the metadata go here, as I mentioned. And then you can read them by opening the array in read mode, and then just printing the different meta values. And that's it. Super simple, keeping array metadata with the actual data. Another thing that TileDB supports is multiple attributes. An attribute is essentially a collection of values stored in the cells. You can have multiple values stored in the cells. In a single array, you don't need to create a different array because you have a different attribute. TileDB is columnar, super important. It stores the values for an attribute in a separate file. Okay, I'm going to show this to you with an example. For example, over here, we have two attributes. One is integer, one is character, single character. Again, the format, and here are the attribute data. You see two different files for the two different attributes here. This allows subsetting on attributes very fast so that you ignore redundant information if you're just reading attribute A0, I'm sorry. And also it leads to better compressibility, because data with the same data type and perhaps similar values have locality, again, better locality in a single file, in a single object, so they get compressed better. So let me show you multiple attributes. For example, here, it's the same array, but we added an attribute over here. This is single character, the type. You can print the schema. You can see this, same idea. Here, the way we prepare the data is that we just add one more vector corresponding to this new attribute that we're writing. And we write by, again, providing the two indices, but then we write an ordered dictionary, one for attribute A1 and one for attribute A2. And that's it. Then you can read it, you get back an ordered dictionary. But here's the cool thing about the columnar approach of TileDB. You can, if you use this notation over here, you're gonna grab the cell values you request with the slicing for all attributes. First, you're gonna get them, and then you can, in main memory now, in the NumPy land, you can subslice, or actually, sorry, in the Python land, you can subslice the attributes from the ordered dictionary. But you can only retrieve a single attribute if you want to. And you do this with a query object here that we use. So for example, this Q1 is gonna bring only A1 from the disk for the query that you have, whereas this one is gonna give you only attribute 2. And you can see it in this example. So if you want to efficiently subset on attributes, you need to use the query object here. Now, we also support natively variable length attributes, which is quite powerful, like strings. This is a string example over here, and I'm going to show it to you also on the notebook. This is the structure again, very similar. The difference is over here. For fixed sized attributes, you just have one file. It would be a0.tdb, but here you also have this a0_var. And a0_var is going to store the actual values, somehow serialized. Again, the serialization I'm going to explain in a bit. But then we want to be able to locate them very fast. We don't want to scan, right? If we, for example, process, the file in parallel, we want to be able to know the starting offset of every value in that file. So the offsets are kept in a separate file. And these are fixed size, so we can locate the fifth cell easily. And then from the offset, we can locate the fifth cell in constant time in A0_var. So very neat architecture. It works extremely well for string attributes and for any other variable length data type. Another cool thing about TileDB is that it supports also variable length dimensions. Remember, this is applicable only to sparse arrays. So sparse arrays can have string dimensions, infinite dimensions, which is very, very useful for specific applications. So it can look something like this. This is a one-dimensional array. It could have been two-dimensional, no problem. This effectively resembles a key value store. This is an unbounded domain. You have infinite gaps here, but in this domain, you can visualize that there is a total order over the strings, especially in this case there is, and each string corresponds to, it has an attribute value. So this is a one-dimensional array. It's gonna look like this, and the idea is exactly the same, guys, with the attributes. Here it is, like you have D0 and D0_var, very, very similar, actually identical to the attributes. And I have an example to show you. So this is for variable length attributes, S0 over here. It's the same idea. This is the only thing that I changed here. And if I go to the, I prepare the data here, I write in exactly the same manner. I just prepare the different NumPy array. And you can see here that I have A0 and A0_var. And also for the string dimensions, it's the same. I set the string type here in the dimension. And then I write similarly to the attributes. I can put d data here, and it's going to understand that these are strings, and it's going to do the indexing and everything it needs to do. And as you can see here, you have the two files for the string dimension. So a very neat architecture, very neat format, and very consistent between attributes and dimensions. You can, the cool thing about the strings is that you can just slice like this, right? You don't need to have a separate vector with a serialization of the strings and the mapping to the indices like what you would do with dense arrays. You can slice natively, like string dimensions. All right. Another cool thing about TileDB sparse arrays is that they admit also heterogeneous dimensions. For example, here we can have a float dimension and the string dimension, both infinite, no problem about that. And this is just gonna work, guys. There is nothing different when it comes to using something like that. For example, I create the dimensions as before: one string, one float, nothing else. And then I write the data as before. D1 has the strings and D2 has the floats. It's the same, and that's why I'm going through them quite quickly. And then you can see here that I have a variable dimension here, variable length dimension here, and a fixed dimension here. So same idea. And then I can slice natively like this. And that's it. It's quite neat. All right. And going back to my original comment, arrays can be viewed as data frames because they're effectively data frames where the dimensions are special purpose kind of columns because they're indexed. Slicing on those dimensions is very, very fast. So they're actually, they can be viewed as data frames. And in fact, we integrated with pandas and arrow and everything so that you get the data back as a pandas data frame and also as an arrow table instead of an NumPy array, just for convenience, because we want to adopt zero copy techniques to do that. We don't want to create the NumPy arrays first and from NumPy to create the pandas object. So here's how it works. So sparse array already exists. This is an array I have created already. And I slice it instead of just this index operator, I slice it with this df object, the data frame object. And what I get back is a pandas data frame. So if I print it, it looks like this, right? This is a pandas object, right? I can use also the query object to do this so that I can subset on the dimensions and the attributes. So here I'm retrieving only D1 for the same query as above. And that's it. Another amazing thing about TileDB and its integrations is that we can also use SQL directly on TileDB arrays through our integration with MariaDB, with embedded MariaDB. So it's as simple as this, guys. You just import this TileDB.sql package. You can see the installation in the docs. And this is it. This is how you read SQL queries from TileDB with MariaDB, and the returned object is a pandas data frame. So here it is. I'm selecting everything from sparse array 1. Here it is. And I can apply a condition here. And the condition is going to work. The condition is going to be intercepted from MariaDB's AST and is going to be pushed down to TileDB. TileDB is going to slice this very fast. It's going to give fewer results back to MariaDB, and MariaDB can continue with its query plan. So very, very powerful. And this shows the integrations that TileDB has and how powerful this can be. Another thing I wanted to show you, and I'm going to stop sharing, is that everything that I showed you here in Python works also in R, in Java, in C++, in all the APIs with the same format. And to prove it to you, I'm going to show you a very simple example in R. So let me do this. So this is R. I have already installed the TileDB R package. I'm going to load the library. Okay, this is embedded 2.4.0. I'm going to create a context. Just a simple example, guys. We have great R tutorials. You can check them out online by Dirk and Aaron. This is just a simple example to demonstrate the interoperability. And here's an array I'm opening. This array exists, dense array 1. And then what I can do is I can just slice the whole thing like that. I can slice a portion, and I can do some more cool things. For example, I can create the object as a matrix. You see the s.matrix equals true here, and this is going to give me a different view like this. Or I can open the array as a data frame, and then I can do this. So a lot of different cool things over here. So check out the tutorials in R and let us know if you need any help with this. But I just wanted to demonstrate the interoperability of TileDB. So going back to the presentation, what about the cloud object stores? So everything that I showed you guys, everything will just work if you replace the array name with a cloud object store URI path. And that's it. There is nothing more to be said for this. Like, it's just going to work. It's going to work fast because of the stuff I'm going to show you in a bit. But that's it. You don't need to change anything else, just the array name and even TileDB for TileDB Cloud, and everything is going to work. That's it. So that concludes the basics. Now I'm going to delve into the layout and the internal mechanics for that to show you a little bit, the power of TileDB and the flexibility in storing data in any kind of storage medium you may have in mind. So the most important concept here is the tiling. I'm going to focus on dense arrays. So a space tile, and I'm going to show you what this is the atomic unit of I/O. So we needed to define some kind of an atomic unit of I/O because we can't just slice 1 byte from cloud object stores or even from the disk. We could, it just wouldn't be wise. And also, as I'm going to show you very soon, we apply compression and encryption filters directly on the tiles. So you cannot just have a single tile for the whole array. You need to block it, you need to chunk it so that each chunk can be self-contained and separate when you access the data. So here's a space tile. These are the extents, like these dashed lines, just to make a point, like what the whole array is 1 tile in this particular case. If we define the whole array as a 1 tile, and if we slice like this, we would fetch the whole array. Because as I said, the tile is the space tile in this case is the atomic unit of I/O. So that would not be wise. But if we define the space tiling smaller, like in this case, then from the disk, from the storage, we would fetch only that tile. So only this light colored blue portion. So tiling is important for fetching fewer data from the disk and therefore increasing performance. But at the same time, the space tiling allows us to lay out the data in different ways, which I'm going to demonstrate. There are 3 parameters that define the layout of the data on the disk. Before I showed you that all the attribute data go in a separate file, right? But I never explained how we sort them on this file and how we chunk them. So for dense arrays, there are three parameters that define this order, which we call the global order in our terminology. First, it's the space tile extents. Second, it's the order, the tile order. It can be row major or column major. And then it's the cell order, which can be row major and column major as well. So here are a couple of examples. So in this particular example, we have 2x2 space tiling, and then row major order within the cell. So you see these arrows, row major within the tile, and then row major across the tiles. So these three parameters create a space filling curve, which is extremely flexible to manipulate. So you can do this instead. You can say, okay, it's similar to this one, but now the tile order is column major. So it goes like this. You see that the curve follows a different path. Or you may say, I want 4x2 space tiles. So the space tiling affects the order, and then row major across the tiles. In this case, it doesn't matter, but column major across the cells. So you see, with just three parameters and the same engine, you can manipulate the order, and the order matters based on your slicing, because the slicing is going to dictate how many tiles you overlap. So how many tiles are going to be fetched from storage. For sparse arrays, it's similar, but here's the idea. We would not be able to do just space tiling because, and then store the non-empty cells in each space tile separately in a tile, because one tile may have had one non-empty cell and another one may have had 1,000,000. That imbalance would create problems in parallelization, in our case, for compression, for parallel I/O, and so on and so forth. We don't like this imbalance. We want the tiles on disk to be of equal size. We want balance there. So we can do that. What can we do? Well, here's what we will do. We will first impose the global order similar to the dense case. Three parameters: space tile extents, then the tile order and the cell order. Same idea. So the space filling curve is kind of computed. But then we would sort the non-empty cells, and then we would group only the non-empty cells based on a new parameter called capacity. So a fourth parameter for sparse arrays, and we're done. So in this case, it's 2. So we follow the curve and we say, okay, 1, 2, that's a tile. Then we continue, then 1, 2, that's another tile. Then we continue, then 1, 2, that's another tile. And we call this a data tile. And that's the atomic unit of I/O. And if I change, for example, what is it here? The capacity from 2 to 4, you see that the tiles, the data tiles become different. They become larger. So the capacity affects how big the tile is going to be on storage, but also visually. We call these rectangles minimum bounding rectangles. I'm going to revisit this, MBR. And the space tiling and the tile and cell order affect the locality of the non-empty cells, and therefore the shape of this MBR, of this minimum bounding rectangle. And that's important for indexing. But these 4 parameters, again, infinite kind of possibilities in how to lay out your data based on your application. And in follow-up webinars, we're going to show you how we chose these parameters, and actually they come with the ingestors. You don't need to do anything about this. You can configure, but you don't need to overthink about it. We have tuned those for the applications. And one more thing that I want to mention is that sometimes for the sparse arrays, this space tiling, because it's very important, it's very difficult to tune. What if one dimension is string? For strings, we don't even have space tiling. Like, we don't support it. How are we going to chunk? And for floats, how are you going to chunk there based on the granularity and the precision? So it's very, very difficult to define those. You can fine tune them, but it's very difficult to reason about them. And that's why we introduced the Hilbert order. And the Hilbert order looks like this, guys. It's a very powerful space filling curve. And you don't have to think about space tiles. For floats, we bin them, right? We check the domain and we bin the domain based on number of bits we're going to use per dimension. And for strings, we do something similar with the first characters in the string. Again, very powerful. You can check it out. And finally, for tiling, again, the atomic unit of I/O is the tile, and this gets compressed as well. I'm going to tell you how it gets compressed in a bit. TileDB allows for more than one filters. It's not just compression. It's multiple compressors, but also checksums and also encryption. These are all filters. They undergo a very specific code path for computing those on the tile. And this is done on a tile basis. But the actual atomic unit of filtering is the chunk, and the chunk is kind of fixed to the L1 cache size. And this allows us to optimize a lot the way we process the filters and the way we have the L1 cache communicate with RAM so that we minimize these interactions. So effectively what TileDB does is it takes the tile, it chunks it further, and then it passes each of the chunks through a pipeline. It could be, for example, Z-standard compression followed by encryption. And this is done in parallel on multiple threads, right? And this is very, very, very efficient in TileDB. All right, so that's it. I can show you very quickly how the filters work, and actually even compression, just for completeness here. Let's do this. All right, so here's how we create a filter list. So a filter pipeline. Here I'm saying I'm going to use byte shuffle followed by gzip filter, and this pertains to a specific attribute and specific dimension. So you can create them separately. A specific compressor of filter pipeline for one attribute, a different one for another attribute. So it is attached to an attribute. So you can see again here the schema. You can see that the filter list has been applied, and nothing else. That's it. I have more information here. I'm going to upload the notebooks for you to see. You can see how to define filters for dimensions and how to use the defaults and all of that. But the one thing that I would like to show you is encryption, because this is quite nice. So the only thing that you need to do is pass a key, a 32-byte key upon array creation. And once you do that, you will not be able to load the array schema anymore. You're going to get an error here. You will not be able to read it at all. You will need the key again. So if you pass the key in the load function, or if you pass the key over here in the open function, you will be able to read the array. So super simple. This is for those that would like encryption at rest. All right, some more advanced topics. Perhaps the most powerful one is versioning and time traveling. So in TileDB, every write is immutable. Remember, every write creates a fragment, a timestamped fragment that will never change. It's immutable, and that's why it's awesome for object stores, because in object stores, every object is immutable. So this aligns very, very well. Again, it's timestamped, and this allows TileDB to do the versioning. Effectively, this is every separate write creates some kind of versioning, and you can move around. You can see views of the array as if some of the writes never happened. So I'll give you some examples. Suppose that this is what we write in the beginning. That's a fragment, a T1. Then we write something else. You can, in dense arrays, you can write portions of the array. TileDB is not going to write anything for this. So it's smart enough to understand, okay, this is only one portion, and I'm going to minimize the amount of data we write for this. Then you can read a timestamp 1 effectively from the beginning of time till timestamp 1, and this is what you're going to see. Or you can read between 0 and now, or timestamp 2, and you can get the updated version. Or you can read after T1 and up until T2, and this is what you're going to get. So superb flexibility here. And the sparse case is the same. It's exactly the same thing. I do a write here, I do a write here, and depending on the time range, I slice different things. The one thing that I want to mention for sparse arrays is that if sparse arrays allow duplicates, and this is specified in the schema, you can see it in the docs, then in this particular case where this write happened and this 40 effectively existed before. So if you don't have duplicates, you're not going to get the previous value. If you have duplicates, you're going to get it. And this, again, for certain applications, is very important to get the duplicates. All right. So I'm going to show you something real quick. Let's see. Dense versioning, for example. So we create the same array again. We write the array. I will get this write info over here. It's an auxiliary function to get the timestamp of this write. I am able to get the timestamp of each write and record it. So I'm just recording this. Then this creates one fragment over here, no problem. Then, and this is how the write info looks like. I can get the fragment name and the timestamp. And then I can open it and read it, no surprises. Then I will prepare some more data and just update this array. I'm going to write again. I'm not going to update. I'm just going to perform another write. So this is going to create another fragment. You see now 2 fragments. And I can read it. I can see that this took effect. And now I can time travel. And I time travel by passing a timestamp range over here in the open function. So here I'm saying, okay, I want between 0 and T1. So I get the original. This is the original data. Or I get after T1, and T2, and this is what I get. And you see these values are just empty special field values. They mean I have nothing there. It's not 0, I have nothing there. Okay, so very powerful to time travel. And actually we have more functionality than this, but this is sufficient for this, for the purposes of this webinar. All right, now in terms of indexing, I have covered a lot around fragments and a lot around dense and sparse arrays. But why is TileDB fast? Because TileDB is more than just a format, right? It's a format, but also an engine that makes slicing very, very fast. So here's how we do it. TileDB has a 3-level kind of indexing approach, if you think about it. The very first one is on the fragment timestamps. So if you time travel, just by the names of the fragments, we can discard. We can say this is not relevant because it doesn't fall in my range. The second is the non-empty domain in each fragment's metadata. Like there is a file, fragment metadata, inside each fragment, and it has the non-empty domain so that we know whether a slice is relevant to this fragment or vice versa. And finally, depending on whether you have dense or sparse, we may use some offset arithmetic for the dense case, and I'm going to show you this, or we use R trees in order to discard tiles. So with the very first 2, we're discarding fragments completely. Don't read the fragments whatsoever. With the last one, we are discarding tiles. And that's why we do the tiling. We do the tiling so that we help indexing, or we can build indexing on top so that we help TileDB discard tiles or disqualify tiles that it doesn't need for the particular query. So the algorithm looks like this, just a pseudocode. I get the list of fragments, so perform a list request, right? Get the fragment names, then ignore fragments that are not in the timestamp that you're looking for. Then ignore the fragments whose non-empty domain doesn't intersect with your query, and then do the rest of the indexing magic on tiles, which I'm going to explain here. So suppose that this is a dense array and it has a 2x2 space tiling. So if I'm asking for this range, I don't need extra indexing. I know that this is dense. I know that these are fixed sized and populated. I know in a dense case that these are going to be populated. I know the order of the tiles. So this one is going to go first, and this is going to go second, this third, and this fourth. So when I slice here, I know that this is the second, and this is the fourth tile from the disk. And I know the offsets. The offsets I keep in the fragment metadata. I keep the offset of each tile so that I can go and grab it. But I don't need an extra index for this. But for the sparse case, remember, there is the global order and the capacity, and those dictate the shape of these minimum bounding boxes of each of the tiles. They look like this. And again, the order is going to shape the tiles differently, but they're going to look something like this, right? So what we do is that we take these MBRs, we put them at the bottom level of a structure, and then hierarchically we group, and that's how we create an R tree. That's an R tree, a bulk loaded R tree. And we just need a top-down traversal in order to slice efficiently and locate which minimum bounding rectangles intersect with my query, because those are candidates for results. We still need to grab them, open them, and check the coordinates to see whether they fall in the slice. And that's it. All right. One of the last topics is consolidation and vacuuming. Super important, super powerful. This merits a separate webinar, which we will do. But I want to give you some ideas here. So the important takeaway is that if you keep on writing to the array, and if you write very small fragments, right, you're going to end up with numerous fragments. And this is going to lead to performance degradation, okay? Because you may lose the locality of the data, and also the listing requests, for example, on S3 are expensive, and they cap the number of objects they return, like 1,000. If you have 1 million, you need 1,000 requests, and those requests are serial. So listing is expensive. on cloud object stores. They're not expensive on your local storage. So you can't afford to have millions of those. So TileDB supports two levels of consolidation. The first is the fragment metadata, and I'll tell you why. And the second is the fragments. So the fragments are straightforward. You're just merging fragments together in the hope to vacuum the consolidated ones and come up with fewer. But the fragment metadata is a much cheaper approach for consolidation, which just consolidates very small information for all the fragments in one file. And you can locate, for example, the non-empty domains. So one level of indexing gathered in a single file so that you ignore fragments very, very quickly. So this is quite powerful and very cheap to do. And all fragments are preserved after you consolidate because you can time travel. You can still have fine granularity for time traveling. We keep them. But if you want to discard them, you can. Right? There is a vacuuming process and you can do it. But time traveling is not going to work after you vacuum, right? Because that granularity for time traveling is lost. So that's it. I can show you very, very quickly something on this. All right, so let's say sparse consolidation. Here's what we do. Same array. We write once. We write twice. Just two writes. You can see the results. You can see the two fragments. What we can do is that we can consolidate the fragment metadata like here. We configure the mode for consolidation to be fragment metadata, and we just consolidate. That's it, very simple. And this is gonna create this file, this meta file. This gathers information about this fragment metadata and this fragment metadata, very small. And that helps avoid gathering the non-empty domain for every single fragment from those separate files. Like it gathers it in one, and then this massively boosts performance, especially on S3. Okay, same data here. If you want fragments, this is the default, by the way. You can just ignore this or set the consolidation mode to fragments. And what this is going to do is create yet another fragment. That's what it does. And the previous ones are preserved. The data is still here. Nothing, no surprises. Time traveling works. You see, this is the original data, so it works. But then you can vacuum the fragments by just invoking this command. This is going to delete the two fragments that got consolidated into this. And the data is still here, but you cannot time travel. And that's it. So I'd like to show you one of the most exciting features that made it into TileDB in 2.3. However, we never announced it, we never showed anything. So I'm going to show you something really cool today. And this is called attribute filter pushdown. So up until now, I told you that TileDB slices very fast. That's fine because it has the index on the dimension, so it slices very fast. But what if I want an extra condition on an attribute? Ordinarily, what you would do is you would slice from TileDB into pandas, and then you would continue with pandas. I'm talking about Python. Like, of course, you can do the same thing in R and other languages, and of course in SQL as well. But what if we pushed that attribute condition down to the engine so that we filter inside the engine before we give you the results? Because just giving you the results may take a lot of time. If it's like billions of records and you just need a portion of it filtered by the attribute, then we're copying a lot of stuff. Even internally, I'm not talking about copying into pandas. We adopt zero copy techniques there, but still we're generating a lot of data for the result buffers, the buffers that will hold the results, right? So can we avoid this? So TileDB supports this attribute filter pushdown. It significantly boosts performance. Much fewer data gets copied around. It's more L1 cache conscious, and we can take advantage of vectorization and parallelism. So these are internal stuff, but it helps us. Like if the user gives us hints on those filters, we can compute them very, very fast internally. So I do want to show you this. This is it. So here's what I did. Okay, I'll post this this tutorial. You can ignore this. This is something internal for optimization of the results, of the result buffers, so that because I'm going to query a lot of data in this particular example. So I downloaded the NYC taxi data only January of 2020. It was 560 megabytes. I ingested it with this command. You can see it documented on the API reference. I made it as a two-dimensional sparse array. These are the index columns. I passed some filters and whatnot. It took 16 seconds to ingest. locally on my machine. I have 8 cores. This is the array schema, like a lot of attributes here. And the total space is 105 megabytes with Z standard. So you can see columnar format and whatnot, like TileDB is very good at that. And then I can read it. I can query the whole thing. So this is what I'm doing. I'm querying the whole thing. It's like 6 million records or something like that. And I'm performing an extra attribute filter here with pandas. And this takes like 4 seconds. It varies if you run it multiple times, it varies, but that's what it is. The total result is 1.6, from 6 million down to 1.6 million. Okay, that's what I did here. Now, I can push this condition. It's the same condition, right? It's the same condition, but I'm pushing it down inside the query. So I'm creating this query condition object and I'm passing it into the query. And I don't need to do any filtering in pandas. I'm just going to store the data in pandas. And the query goes down to 1.3. So massive performance difference. Actually, one here, 2.2 versus 3.9. And then I can do also end conditions. I'm sorry. We support only end conditions for now on different attributes, same attribute doesn't matter, but very soon it's going to be more, and it's going to be more complicated expressions. This is just to make a point that the technology has been built, and now it's a matter of supporting more conditions down into TileDB. But this provides significant boost, and we will try to do even more, like push down group bys, joins, and so on and so forth, but primitives at this stage. And the last super exciting feature that shipped with 2.4, like today, is this schema evolution feature that a lot of people have been asking for. So it's ready, and I'm going to demonstrate it. So this allows us to alter the schema. And for now, we can only add or drop an attribute. But in the future, imagine that anything will be changed, can be changed, like the capacity, the tiling, everything, right? And this is versioned. That's why it took us that long. It's versioned. You can time travel. You can do everything you want, as you did with the rest of the stuff that I showed you, but now on a different schema. More features are coming up, full version time traveling supported. So let me quickly show this to you. Let's do this. So same array as before, one attribute in the beginning. We write some data to it, right? This is the schema created. Remember from creation of the array. This is how the data looks like, and this is what I slice. I'm sorry. This is version. I want schema evolution. I apologize. Up until there, it's exactly the same. It's exactly the same. And here is what I want to do. I want to change. I want to create a new attribute, and I want to add it to the schema. So before I had only A. This is what I had before. And I'm adding one attribute, which is int 8. Doesn't matter what it is. So if I print the schema now, I can see both those attributes. And if I slice the array, I get some fill values here because A2 did not exist in the write that I performed before. But still, now I see it, and I get some fill values back, which is the correct behavior here. And if I check out the contents of the array, you can see I have 2 files for the schema now, both timestamped, right? Because I changed the schema. I can perform another write to this array, and then I can slice it, and I can see that this write took effect. And for the newly written values, I provided 2 vectors, right? One for the first attribute and one for the second attribute. And this worked perfectly. And I can drop an attribute. So I can drop the first attribute now if I want to. So very simple. Schema evolution object, drop the attribute, and then evolve the array. So the schema has evolved. I see now only the second attribute. I don't see the first. And then if I slice it, I only see the first attribute, the second attribute. And that's it. So this is how schema evolution works very, very easily. And we're hoping to put more features into this feature. But this works today with 2.4. All right, guys, I'm done with the examples. I'm just going to touch upon a little bit on writing, a little bit on reading, and the work in progress and competitors, and then we will be done. So notes on writing, lots of flexibility with orders. Like if you use low-level languages like C++, you can boost the performance of ingestion. That's what we do in many, many applications. Everything works in parallel in a lock-free manner. You can have multiple workers writing to the same array. There are going to be no conflicts, no consistency issues. We do not support deletions and updates just yet, but these are going to appear in very soon in later releases. Some tips for performance: the tile should be big enough. I don't know, 100 kilobytes to 1 megabyte. It depends on the application. It requires a little bit of tuning. Don't make it too small. Compression is not going to work. Don't make it too big. When you slice, you're going to bring too much information. So there is a trade-off. Each fragment should be about 1 to 2 gigabytes. So consolidate. And again, I'm going to have a different webinar for consolidation. Fragments should not interleave. So the non-empty domains should be kind of disjoint so that indexing kicks in. And do run fragment metadata consolidation often, because that's going to boost the performance on S3 a lot. Like without having to do too much fragment consolidation, just the fragment metadata consolidation is going to work well. Some notes on reading: TileDB is eventually consistent. This means that you can have reads and writes together, no problem at all lock-free. But when you perform a read, you open the array and you see only committed fragments with the .ok file appearing there. It's not going to see anything else. And the read is not going to be affected if another write commits. It's just not going to see that write. But if you redo the read later, you are going to see that write. So this means that it is eventually consistent, right? Because S3 as well, at the time of the creation of TileDB, was eventually consistent. Now it is introducing more stronger consistency, but we want for now to tell people it is eventually consistent because we're lock-free. This gives you a lot of flexibility when writing and reading in parallel. We do support reads in different layouts. Again, if you are a more low-level kind of programmer and you want performance, TileDB gives you different layouts to optimize performance. We support streaming reads. This is super difficult to pull off. The reason being that in the dense case, you know what to expect. Like you know that, okay, I'm expecting 1,000 cells, so I can allocate my buffers appropriately. But if you have variable length attributes and if you have sparse arrays, this is difficult. How much are you going to allocate if you don't know how big the result is? So we have this feature. I'm not covering it here, but you can do stream reads. Things are not going to fall apart. Some tips for performance: allocate sufficient space for your buffers, like what I did in one of the examples I showed you. Again, different webinars for that, for optimization and performance. Tune the read and layout based on your reads. So try to imagine, what am I reading? How do I slice? Is it a square-like slicing, rectangular slice? What is it? So you can tune the layout upon array creation based on your reads. And push down slicing and attribute filtering as much as you can, because this is what TileDB is extremely good at. All right, a little bit work in progress. More schema evolution features, support for deletes and updates. You're going to see this very soon. Git-like versioning. I'm very excited about this particular feature. It can be done exactly because of the way we work with fragments. Fragments are gonna give us that feature, like very easily. ACID, we're going to support ACID by modularizing locking. So again, we want to make everything work as good as possible, avoiding locking for as long as we can. Like, this is a conscious decision. Locking should be done only at the particular instant where some synchronization is needed. And we're going to compartmentalize that only for those that need this particular feature. And this feature should not affect the performance for the rest, because 99% of our use cases are lock-free. They don't need this kind of ACID guarantees. So more tile filters, you're going to see some min, max, and all of that stuff. You're going to see more push down. This is going to help more push down operations like aggregates. You're going to see some RLE and dictionary compression for strings. This is very important for some of our use cases with string dimensions. It's going to also allow us to compute on compressed data. We don't do it now. We know how to do it. This is common knowledge for columnar databases. It's just that it wasn't in our roadmap, but now we're getting there. We're going to start more sophisticated computations like linear algebra. You're going to see some progress very, very soon. More SQL push down. We don't envision to build the whole engine because we integrate with other engines, but some push down is going to help those engines. Like if you push some portions of the query plan of the database to storage, the performance is going to be boosted. And finally, graph algorithms. Again, you're going to see this. We had an amazing hire on this front. So you're going to see more stuff on graph algorithms as well. All right, and these are the last couple of slides. I'm gonna give you a very high level. I want to emphasize on this, very high level comparison to other formats for those that have used them and for those that know them, just so that they understand after seeing this webinar where we kind of stand as opposed to those competitors. So HDF5 is one of the projects that I love, and it inspired me to create the original TileDB version when I was researching on this. So HDF5 is awesome. TileDB is cloud native versus HDF5. When I say cloud native, I mean that all the architectural decisions are around the cloud. HDF5, most of the architectural decisions were around distributed file system like Lustre, single file, high performance computing, supercomputing, and so on and so forth. So very different targets from an architectural point of view. The other thing is that TileDB has support for arrays. And finally, TileDB has support for versioning and time traveling. So these are the three features that you would choose TileDB over HDF5. For the dense case, they're kind of the same. But for the sparse case, cloud, versioning, you would prefer TileDB. So ZAR is another very exciting project. ZAR is built in Python. There are plans for C++, but currently it works in Python. TileDB is built in C++, so we offer these tons of interoperability, not only Python. Again, TileDB has support for sparse arrays, and TileDB has support for versioning and time traveling. Super important features for our customers and users. Then for data frames, I'm pretty sure that everybody knows Parquet. And Parquet is very simple. It's a columnar way of storing data frames, which is great. TileDB is columnar as well, so a lot of similarities there. But TileDB is multidimensional. So in Parquet, you will have to hack it, like partition it, create multiple files, folders, like what Hive does and what Spark does. You have to hack it. It doesn't come with a format. The format is just a blob, right? A blob of values serialized in a columnar way, chunked, compressed, and so on and so forth. TileDB is much more than that. It allows you slicing, flexible orders, and so on and so forth. Parquet also is just, again, a blob, like you would use it for data frames, not for multidimensional dense arrays. There is no concept of slicing multidimensionally and identifying where the dense cells are. And TileDB has native support for versioning time traveling. Again, you need to hack Parquet to do that. And Delta Lake did exactly that. You hacked Parquet to do this. So again, TileDB is natively multidimensional, right? Delta Lake has some support for Z order and stuff like that, but with TileDB, the opportunity to lay out the data in different ways is just massive. Also, TileDB doesn't rely on anything. It doesn't rely on Spark or Presto or any other subsystem for synchronization and whatnot. TileDB is completely standalone. TileDB has support for dense arrays. This difference stems from the fact that Delta Lake is based on Parquet, that's all. And finally, just to be fair, TileDB doesn't support updates and deletes or ACID-like semantics, and Delta Lake does for data frames. We want to build it for everything, because the engine is universal. So once we build updates, deletes, and ACID for the engine, then even dense arrays inherited, not just the data frame. So, but this is coming up. All right, with that, thank you very much. It has been long. Thank you for bearing with me. And yeah, Mike, I'm ready to answer any question. I'm here, so let's do it.
The first one, are the arrays pandas or like pandas? Can I kind of learn or pick up what to do with TileDB arrays by studying pandas tutorials?
Yeah, good question. So the API of TileDB is very similar to both pandas and NumPy, but much smaller because at this point it just slices. I'm going to show you something more in a bit, but it just slices. So once you slice, the data is in your environment, either in a NumPy array or a set of NumPy arrays or pandas. From that point onwards, you can continue doing whatever you want. So remember, the storage engine that I'm presenting offers very fast slicing, bringing data back into your environment.
Any tips on storing LiDAR data? I want to store all of the UK's height data and then query for small tiles at a time.
Yeah, excellent. So we do have a LiDAR workshop online on our events page where Norman is showing a lot of cool stuff. We have an ingestor by using PDAL. So you don't need to again, overthink it. That creates a sparse three-dimensional array where X, Y, Z are double coordinates. And then you just slice. Like everything that I showed you will just work. And then you can do anything you like with NumPy or pandas or GeoPandas and so on and so forth. I do have a couple of tips that I'm going to cover also in one of the slides that I have. When you write, make sure that each of the fragments, so each batch, and this is configurable also in our PDAL connector, create each fragment to be at least 1 gigabyte, because I know it's going to be a lot of data. Like if you have small LAS files, ingest multiple LAS files into one fragment. Don't create too many fragments. And also, if you can, try to create ingest in a single fragment, so in a single write operation, geographically disjoint portions of your data set. So each fragment, if you can visualize the 3D bounding box of that fragment, the non-empty domain, those non-empty domains should be as disjoint as possible so that TileDB's indexing kicks in. We will create a separate webinar for that, delving into performance and all of that. But I think this piece of information is going to get you going.
Is it possible to, implement tiling using, the X, Y, Z kind of dimensions of LiDAR data? Same question goes for images, like, raster data sets.
Okay. So an important point to make again, TileDB is a flexible array engine. You can tune it to any application you want as you like. We just abstracted all the difficult engineering, all the magic, so that you don't have to redo it when you do LiDAR versus when you do imaging. It's the same engine. It's the same principles, right? Now, for LiDAR, empirically, we saw that Hilbert curves with a bounded domain, like the domain of the array, as close to your points as possible, so that the Hilbert curve kind of preserves the locality, but also splits the data enough along the curve so that you can index better and you can create more meaningful minimum bounding rectangles. It's very easy to do through PDAL. Like we have optimized it, we have tuned it, we have tuned the capacity, we have tuned everything. So 3-dimensional sparse arrays, double coordinates. That's it. For imaging, it's gonna depend on your slicing query size. Probably it's gonna be some kind of a square. If it's square, so the space tile extents must be square-like. And then it's gonna depend on how much data do you foresee to slice at a time. Is it gonna be a megabyte or 10 megabytes? That's gonna dictate how big the tile extents are gonna be, so that you tune it to the performance. You can, for example, if you do 2x2 space tiling and your query is huge, it's gonna bring 1 million tiles. And for every tile, there might be a little bit of latency internally because we do something, we allocate an object for it and so on. So like there are some non-negligible costs that are going to pile up if we're talking about millions or billions of tiles. So ideally, your tiles should fit more or less your slicing patterns. And you know those slicing patterns. It's not like for an application, it's kind of fixed. And that's why we tuned the ingestion for PDAL, we're tuning the ingestion for images, and you can ping us, we can give you some scripts. We tuned it for genomics and so on and so forth.
Great. This next one, I don't know how much we can share, but they're asking about the crypto algorithm that we use for encryption at rest.
Yeah, it's in the docs. AES 256 in the GCM mode. That's what we're using.
Great, thanks. So in time traveling, you indicated that the time period at open, so does that mean I would need to close and reopen if I want a different period?
Yes.
Okie doke. Can I store a gigabyte of data using a dense array?
So of course, probably you mean a blob, right? Like just a blob. The way I would do it would be, again, it depends on your slicing patterns. Like, do you just want to store it in order to stash it on S3 and just grab the whole thing down? That could be just a key value, like a value in a string value kind of array, right? It could be, if you want to slice it, compress it and slice it. That's in one-dimensional dense array. So every byte, like you can create a dense array where with a single attribute, where the attribute is a byte int 8 or uint 8 data type, just store it there and then compress it and do everything that we do, versioning and whatnot. And then that will allow you slicing subsets of this file very, very fast from S3. So yes.
Will you eventually support non-heterogeneous dimensions for dense arrays, or some mapping from labeled dimensions to the integer dimensions, as in like X array?
Yeah, that's another great question. So you mean heterogeneous, right? Or not non-heterogeneous, not non-homogeneous. So the answer is yes. Effectively, you can do that today, by the way, but it's not automated, right? You can create a dense array, and then you can create a mapping between a string and an integer. If you want string labels, that's your label array, string to anything. That could be more complicated, more sophisticated than that. It could be a data frame. It could be something that has a string and a float and whatnot, and then one attribute is the indexing information mapped to the array, right? So you can do any query on that data frame to grab the index, the dense indexing, and just do the index slicing in the dense array. So absolutely, we just need to automate this. So XArray is a good starting point. We feel that it's going to go a little bit beyond that because we don't want the labels to just be stored in main memory. This we can do very easily. The question is, what do we do if the slicing conditions are more complicated than just grab the whole labels into an NumPy array and then I'm gonna figure out where the indexing is. We want to do that out of core in case the arrays are massive and those labels are massive as well. So we're just looking into APIs, and it's a matter of time that we will do it.
How does space tile or how do space tile parameter choices affect tile output files?
Why don't I show you an example? Like these values, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth, right? They go here in this file. It's the same file, but I never, like in this slide, I have not mentioned the ordering. Suppose you have one tile, meaning that the space tile is 4 by 4, and the cell order is row major. So this file will contain 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. And then if you have filters, it's going to compress them and put the result into the file. That's it. But if the space tiling goes 2 by 2, or I'll make it easier, I'm going to do it 4 by 1, okay, 4 by 1, then you would store 159313 compressed again in the file, then 261014 compressed in the file, and so on and so forth. If it goes 1 by 4, you would store 1, 2, 3, 4, but compressed with metadata and whatnot. Then 5, 6, 7, 8 compressed. Then 9, 10, 11, 12, and so on and so forth. So space tiling affects this a lot.
So this next one, can I ingest gigabytes of data in S3, and will the metadata created also be stored in S3? This person might have actually mentioned that you sort of address this, but you can kind of go ahead and just answer that.
Yeah, the TileDB format is self-contained. It's that folder that I showed you. It goes on S3, similar to your disk, and you don't need anything else. It's there, it's on S3. So whenever you want to slice it, whether it is from your laptop or from an EC2 instance you spin up in the same region as the S3 bucket for performance, everything is embeddable, right? Like everything is serverless. You don't need a server. There's no server like Hive. Like you don't need a metadata store to help you guide your way into the data. So the data, metadata, system metadata, everything stored in that folder, and it is the TileDB engine's job to know which files to look up first to get the indexes in order to start slicing the data.
How does slicing perform when there are many versions, especially skipped versions, that don't have writes within the range of the slice? In other words, are they selected? Are they skipped, or are whole versions skipped?
I think I covered this on the indexing slide, but I will repeat, no problem at all. So here's how it works. Let's forget about time traveling for a little while. Suppose that we have 5 fragments, and suppose that we want to access all 5 fragments. Like time traveling is from 0 to infinity. Like I want everything that happened, regardless of the version. The way things work is that we list, so we get the names. We see the timestamp, okay, qualifies, nice. So all of them are up for querying. And then we get the non-empty domain from the fragment metadata or from the consolidated fragment metadata. So I know the bounding box of this, the bounding box of this, and so on and so forth. And I have my slice. And it doesn't matter if one qualifies or not, any subset, all or any strict subset of those will be selected for the query and say, okay, let's say in this case that only those two are selected. These are ignored because they don't overlap my query. They're definitely not qualifying for a result. So I'm going to focus on those two. And then in the sparse case, for example, I grab the R3 from the fragment metadata. I'm bringing it to main memory. And then I'm checking which tiles intersect with the slicing. Now let's do time traveling. And time traveling is between this one and this one, just suppose. So again, we do the same thing, list. The very first thing that we see is that the time traveling is between this one and this one only. So I disqualify this, I disqualify this, I disqualify this completely. I don't even think about them, and I focus on these two. I get the non-empty domain of this, so request, non-empty domain for this request, and I see which one overlaps. Like if this overlaps, I consider it. If this does not overlap, I will just disqualify it, and that's it. And then I'm going to go into the tiles and so on and so forth. So it works as if the fragment was independent. Like think about it like this. It's just that TileDB is quite smart, especially in the dense case. For example, if one fragment completely covers the non-empty domain of another relevant fragment, still I know that this is going to overwrite this. So I disqualify this. So there is a lot of sophistication internally on how to prune fragments, how to prune tiles. Actually, the whole engine is architected around those decisions. How do I prune fragments fast? How do I prune tiles within fragments fast? And time traveling is yet another way to prune. Like think about it like this.
This is the last question we'll cover. And I should note that it's 2 parts. I'm going to read it in full so you have the context, but don't worry about answering the first part because we've already answered it with the eventual consistency model. 1, how does TileDB support parallel read-write to a single array from multiple threads/programs? What about the array's locking scheme? We covered that. And then 2, will it support features such as data update notifications to array subscribers, like Redis, for instance?
Yeah, anything that has to do with pinging some kind of a service, locking is one of them, by the way, right? That's why locking has to be kind of outside of the storage engine. It's a service, like because multiple on the thread level, you can lock. It's fine. We can have thread safety there, and we have thread safety for everything. Process safety, especially with multiple machines, you need to ping something, a service. That's the lock. Same thing with notifications. You need to ping somebody who has the overall view of what's happening. And that's why we built TileDB Cloud. I'm not mentioning it in this webinar only because I wanted to focus on the open source stuff, but anything that has to do with automating a service, that's TileDB Cloud for. And if this request comes up a couple of times, we're going to put it in our roadmap. I understand exactly what that would entail. It's just not on our radar at this point.
Great. Well, I think we've answered all the questions. So I guess I'll just end with a final thank you from me, and Stavros, if you want to say your goodbyes.
All right. Thank you very much, everyone, for attending and all the interesting questions. Once again, all the credit goes to the team. The team worked extremely hard. It works extremely hard in general, but it worked very, very hard for this webinar to come out today in time and with a 2.4 version out. So a big thanks to the team as well. And looking forward to seeing you guys on our Slack community or seeing emails from you with questions and comments. So thank you very much.